question on Doppler effect, and before we tackle this, let's look at some details of Doppler effect first. So here I'm not going to be explaining exactly what Doppler effect is. You should already know what that is. I'm going to explain how to work out problems, or how do we deal with the quantitative part, the numerical part of Doppler effect. Well, in short, Doppler effect is, what is it? Well, notice that I told you that frequency of any source purely depends on the source itself, and when the wave travels from one medium to another or anything, the frequency remains a constant. However, if the listener and the source are moving relative to each other, then the listener will hear a completely different frequency than what the source is emitting, and that is what we call as the Doppler effect. Okay? Alright, so why does that happen? That happens due to the relative motion between the two. Okay, so let's try and understand this way. Suppose I have a case where the source is moving, source moves, and the listener is stationary. Listener is stationary. In this case, what's going to happen is, as the source is moving, it's producing waves. The waves are going to look somewhat like this. If I were to draw two-dimensional waves, the waves are going to look somewhat this way, like so. And therefore, if it's traveling this way, and therefore you will see the wavelength would have shrunk on one side and the wavelength expands on the other side. So the side where it's approaching the listener, the frequency is going to increase. The side where it's going away from the listener, the frequency is going to decrease. So the frequency heard by the people will be different when it's approaching and when it's receding. So the reason why Doppler effect takes place in this case, so the reason for this is because wavelength changes. Okay, so that's what happens when source is moving. Now remember, motion is a relative term, so moving with respect to what? Well, source moves with respect to the medium. That's what I'm talking about. With respect to medium of the sound. So the medium, so usually it's going to be air. So when I say listener is stationary, it's stationary with respect to medium. So that's one case in which you can have Doppler effect. Another case in which you can have Doppler effect is source is at rest, again with respect to medium, and listener is moving with respect to the medium. In this case, since the source is not moving, the waves are going to look symmetrical on either sides. But since the listener himself is moving, well, you can just imagine when the listener moves towards the source, more waves are going to hit him per second. In other words, the velocity of sound as seen by him increases. And that's what causes the change in frequency. So here, wavelength doesn't change. The wavelength remains the same. If you could see the wavelength, you would see the same wavelength, but it's the relative velocity of the sound that changes. In other words, you can say there's wind blowing, and because of the wind blowing with respect to him, so if you move this way, the wind blows this way. So the wind is one that gives the sound additional speed. So the reason over here is because the velocity of sound increases or changes, but the wavelength is same. Wavelength is the same as the emitted wavelength. Okay, so these are the two cases, and then you can have both the cases happening. We can have source also moving with respect to the medium, listener also moving, and both of the effects get multiplied or added up together. So what is the one master formula that's going to tell me what's going to be the frequency in all the cases? And the way I like to think of it is this way. Imagine you have a source and you have a listener over here. Okay, I'm going to call listener as O for observer, and S for source. Okay, so imagine we know what the velocity of the source and the observer are. Okay, then the apparent frequency registered by the observer or the listener, I'm going to call it as F prime, is going to be equal to f, that's the original frequency, into v, vo, v, vs. In the numerator, it's the observer's motion that plays a role. In the denominator, it's the source motion that plays a role. You have to somehow remember this. And the way I like to remember this is, I remember the formula F equals V over lambda. And I remember, okay, in the numerator, velocity of the sound is what comes in the numerator. And that changes in which case? Oh, it changes due to the motion of the observer. And that's why the observer's effect is coming in the numerator. And denominator has lambda, and lambda changes due to whom? Well, lambda changes due to the source moving, and therefore the source motion comes in the denominator. That's how I like to remember it. And it's kind of true, I think. Yeah, it is kind of true. That's the reason. But anyways, and then you can have a plus or minus signs. So we can build 4 equations by using these combinations. So once you remember which one is the observer and the source, this is how I remember. You can try and remember it that way. Then you can also remember it's very easily whether it's a positive sign or negative sign. So let's try and do it this way. Let's take an example. Suppose I say that the source is moving towards the observer and the observer is at rest. Observer is not moving at all. What's going to be the apparent frequency? Well, the apparent frequency is going to be the actual frequency emitted by the source multiplied by V, and V0 is 0, there's nothing in the numerator, divided by V and Vs. Now we need to first ask ourselves, what's going to happen when the source moves towards the observer? Is the frequency going to increase or the frequency is going to decrease? Well, the waves are going to shrink, as you have seen over here, right? When it's approaching you, the frequency increases. If the frequency has to increase, the denominator must decrease. And therefore, we put a minus sign. That's how I remember this. Okay, let's take another case. Let's take a case where source is moving away from the observer and even observer is moving away from the source, and they have some speed with respect to the medium. What's going to be the frequency heard? Well, the apparent frequency is going to be the actual frequency divided by V, and numerator is observer because observer changes, the velocity effect is due to the observer, and the wavelength changes due to the source. Now what I do is I say let's forget about observer for a while. So let's concentrate on the denominator. The source is moving away from the observer. What's that going to do? Well, if the source is moving away, then you're gonna be somewhere over here, so the wavelength increases and the frequency decreases. So when the source is moving away, if something is moving away from the something, so whether observer or source, if it's moving away, the frequency decreases. So in order to decrease the frequency, what should I do to the denominator? The denominator should increase, so I put a plus sign. Now let's consider the observer. Again, observer is moving away, that causes a decrease in the frequency. What should I do to the numerator to decrease something? Well, I should decrease the numerator, I should put a minus sign. And that's how I remember this. Okay, and one last thing, remember these velocities are the components of the velocities along the line joining the source and the observer. Meaning, if for example I had a case where source was moving this way and the observer is moving this way, then what I should do is I should know what these angles are. Let's call this angle as alpha. Let's call this angle as beta. And what we're going to substitute now is not the entire velocity, but its component along the line joining the two. So we're gonna say Vs in our case for Doppler effect is going to be whatever this is velocity. Let's call this V1 and V2. So the Vs is going to be V1 cos alpha, and that's what we're going to substitute over here. And V0, which we're going to substitute here, is going to be V2 cos beta. Its components. Okay, it's the component along the direction of the line joining them. That's what matters. Alright, so this is how you deal with Doppler effect numerically. Let's do the problems in the next episode.